Hi guys, so in this lesson we're going to continue looking at the characteristics and properties of waves and parts of waves and stuff. So yesterday we talked about what a crest and a trough is. So our crest of our wave is up here at the top of the hill. Our troughs of our waves are at the bottom. You'll always see this like midline of the wave. So you can always identify the crest is going to be above that midline and the trough will be below that midline. Now, we have a few different ways to measure waves. There are different characteristics that we can measure about waves. So the first characteristic that we can measure is called amplitude. So amplitude is what we call the power of the wave. This is measured from the resting position, which is that midline of the wave, and then up to the crest, or you can do from the midline down to the trough. Okay. So on this first example here, we have a high amplitude that is measured. It's a very long distance from that midline to the top of that crest. Whereas in this example down here, we have a low amplitude, okay? We have a very short distance from our midline to our crest here, okay? Now, usually higher amplitude waves mean that there's going to be a higher amount of energy associated with that wave, whereas the lower amplitude, there's going to be a lower amount of energy associated with it. Another thing that we can measure about the waves is their wavelength, which is usually represented by this Greek letter lambda, okay? So it kind of looks like an awkward little H in a way. So you guys will have to get used to writing out that symbol when we're talking about waves. But wavelength is the horizontal distance from a crest to the next crest or from one trough to the next trough. So this top example here has a very long wavelength. Okay, we've got a long distance between this crest over here and this crest over here. Okay. Now this bottom one, we have a very short wavelength. So we have a very short distance between our two crests. Now, the relationship to energy here is a little opposite from our amplitude. So when we have very long wavelengths, that means that we don't have a lot of waves happening. So that means that there's not a lot of energy. So long wavelengths have a low amount of energy associated with them. Whereas short wavelengths, that means there's a lot more waves happening in that time period, so that's going to have a higher amount of energy associated with it. Okay, so long wavelengths have low amounts of energy, short wavelengths have high amounts of energy. We can also measure what's called the period of the wave. So the period is the amount of time that it takes to complete one cycle. So this would be a single vibration or a single wave. Okay. So this is basically the amount of time from one crest to the next crest. So how long it takes to get from one wave to the next wave. So the units for period are seconds per wave. So it's how many seconds it takes for each wave to pass. So this example here has a pretty long period. It takes 2 seconds to see each wave. One wave is happening every 2 seconds. Now this example down here has a period that is half as long as this one, okay? Because there's a shorter distance between the two waves. Okay, they're happening a lot more often, so each wave is coming about every 1 second. So it takes 1 second for each wave to pass, whereas up here it takes 2 seconds for each wave to pass. Okay. Now, in terms of energy, okay, this top example here, okay, we've got that long wavelength again. So that means that we're going to have not a lot of energy associated with this example up here. Whereas this shorter period, we're going to have higher amounts of energy because we see more waves and it has a much shorter wavelength between the two crests. Now, frequency is usually mixed up with period. Okay. Frequency is kind of like the opposite of period in a way. So frequency is the number of cycles or waves that occur in 1 second. So this is measuring waves per 1 second, which can be converted into hertz, which is probably a unit that you've heard used in like measurements of radio waves. So the radio channels, although I don't know a lot of people that listen to like actual radio anymore, most of us are streaming stuff now, but in your car, when you press one of those radio stations, those are measured in hertz. Each of those numbers for those stations is the frequency of the radio waves that give you that channel. So we can use that frequency to measure any kind of wave. Like I said, that is how many waves happen per 1 second, whereas your period was how many seconds it takes for one wave to pass. So in this top example here, we have a very low frequency, okay? Again, we've got that long wavelength, very low frequency. In 1 second, we only see one wave pass. So that would be equal to 1 hertz for the frequency of that wave. Now, the second example, we have a very high frequency. So in 1 second here, we actually see 2 waves pass in that single second. So that frequency would be converted to 2 hertz. Okay. So again, in terms of energy, if we have a very low frequency, we have a very low amount of energy because we see not as many waves and the wavelength is a lot longer. Now, if we have a very high frequency, then we have a very high amount of energy because we see a lot more waves in that time period and we have much shorter wavelengths in between each wave. So period and frequency are very closely related to each other. Okay, they are what we call reciprocals, which is the fancy math word for opposites. You may have heard that word in a math class before. So basically what that means is if you have one of those values, you can still calculate the other. So if we have a period, we can still calculate the frequency. Or if we have a frequency, we can still calculate the period of a wave. So the way that works is our period, okay, is the number of seconds that it takes for one wave to happen. Okay, that's how we calculate period. Okay, now if we had our frequency, okay, we could do 1 divided by our frequency in order to get that. Okay, so this is going to be measured in seconds because that's how we measure a period, is how many seconds it takes for each wave to happen. So if we take a look at this wave example here, okay, we want to know the period, okay. So this is the measure of the period here, okay, how many seconds it takes for one single wave to happen. But the only thing that we're given is that there's this many waves in 1 second. So we're given the frequency, okay. We know that there are 1, 2, 3, 4 waves in this one single second. So we can take that and calculate our period. Okay, so every 1 second we see 4 waves. So if we do 1 divided by 4, because that's our frequency, okay, we get 0.25 seconds per wave. Okay, so 1 divided by 4 is 0.25. So that matches up with what we see in our diagram because in one wave, okay, it takes only 0.25 seconds. Okay, if we break down that second into 4 little chunks, we get 0.25 seconds. Now for frequency, okay, to calculate the frequency, we have to count how many waves happen in 1 second. Okay, so we did that already with our first example, okay, but let's pretend that we don't know the frequency at this point. We only have the period. We only know that our period is 0.25 seconds per wave, okay. So we can take 1 divided by our period, and that will get us our frequency, which is measured in hertz, okay. So we see 4 waves in that 1 second, okay. So frequency is going to be equal to our 4 waves per 1 second. That equals 4 hertz, okay. Another thing that we can measure is wave speed. So wave speed is a measure of how fast a wave is moving. So for mechanical waves, it's actually going to depend on the state of matter that the wave is traveling through. So remember, mechanical waves are the types of waves that have to have a medium in order to travel through. Okay, they cannot travel through a vacuum. So generally, they're going to travel slowest through a gas. Okay, and mechanical waves will actually travel faster through a liquid, and they actually travel fastest through solids. Okay. So this is why when you see fireworks out in the distance, okay, you see them before you hear them, okay? Because you seeing them, that's an electromagnetic wave. That doesn't need a medium to travel through. It can travel as fast as it needs to no matter what. Now the sound waves though, that's a mechanical wave. And that takes a little bit more time to travel through a gas, which would be the air around you. Okay. That's also why you can hear sounds a little bit easier in stuff like if you put your ear up to a door or something like that, trying to eavesdrop on a conversation. Okay, when you get close like that, those sound waves travel a little bit faster through that solid. So then that way it makes it a little bit easier to hear. Now, it obviously does depend on the material, the actual construction of the material and stuff. So traveling through a door versus a cinder block is going to be a lot different for that. Okay. We can calculate wave speed though by taking the speed, or we will get the speed by taking the wavelength of the wave and multiplying it by the frequency of the wave. So that's how we can calculate how fast that wave is going. All right, so I think that's where we're going to stop for today. We are going to wait to get into the more connections between waves and energy in our next lesson. So make sure that your notes for the parts of waves and measuring waves are filled in, and make sure all the questions in this video are answered, and then make sure the video gets submitted at the very end so then your grade gets recorded. And I will see you guys tomorrow for our next lesson.